to produce GABA, we need to have an action potential. So you want to release GABA into the synapse. Seriously, for each one of these, if you were to walk through and literally draw it out, take the time, I mean, that would take you an hour to get through that figure, which is a very hard figure to digest. But the goal here is to release GABA. GABA is going to inhibit the target, but you have to release it. The only way you can release it is to excite this neuron. Does that make sense? Does that answer your two-parted question?
Yeah, well, I was thinking, like, does the excitatory one have to be?
It has to be excited.
So is
what?
it implied that it would be excited by something else?
Yes. What you have to remember is there is no signaling pathway in your brain that's isolated. So here's substantia nigra, all right? A signal came to substantia nigra that said, hey, do something. It then sends a signal up to the striatum. Now, it's either going to be a signal that affects the direct pathway or a signal that affects the indirect pathway. Depends on what's excited. But you need an excitatory signal that is going to lead the target to undergo a new action potential. Now, if the target is inhibitory, that will lead to inhibition. If the target is excitatory, it will lead to excitation. So you have to, a given in here is if inhibition doesn't happen, then excitation. If I don't inhibit the thalamus, it's going to produce glutamate. There's so many signals coming into the thalamus. However, do not make the mistake of saying lack of it. If this is not excited, then this will excite this. No, that's wrong. All this can do is inhibit. So there are so many levels of signaling going on prior to this that any given neuron in the brain has probably hundreds of synapses taking place. And those synapses are going to be involved with either guaranteeing an action potential, because once you have an action potential, it's all or none, or inhibiting an action potential, keeping it in hyperpolarized state. Cool? Yeah.
Where is the enkephalin? Oh, sorry.
Yeah. Yeah, I just spelled it all
So
out.
there are
for you.
three of them that are inhibiting. It's like glutamate,
Glutamate is excitatory,
oh,
all right?
sorry.
Dopamine is always excitatory or inhibitory, depending on the target. GABA, substance P, and enkephalin are the inhibitory neurotransmitters in this pathway. We're gonna proceed to neurotransmitters in a minute. I really would suggest working on this very in detail, because this signaling coming in here is involved with Parkinson's disease, Huntington's disease.
What I can see is that has to be like two inhibited 2 times, and then
What are you talking about?
like a GABA and enkephalin inhibited the GPE, like and then,
Okay.
and then
Once this is, okay, if this is inhibited, does this happen?
nothing happened.
No, it doesn't happen. Therefore, this will excite. There are other, there's no, if we put all of the signaling pathways on there, there wouldn't be room for you to see anything. The whole point here is, this is stressing the inhibitory events that cause a lack of signaling, so that the signaling coming out here will be inhibitory. If you do not inhibit a pathway, there are enough signals coming to it that excitation will happen. Yeah. So, okay? You really have to walk through and look at what's happening here. Like I said, we get to Wednesday and we're going to be looking at about 10 or 12 different movement disorders, most of which involve the pathways coming through you. Earlier in the semester, we looked at figures like this table that walk through a whole variety of neurotransmitters. And this becomes important once again. You have access to these in the past. I'll make sure these go up again today, because it really explains excitation and inhibition again. So here we have acetylcholine. It's excitatory, okay, in the central nervous system. Two important events: direct action and indirect action. Direct action means that the acetylcholine will bind with a receptor. And that receptor will open a channel, and you'll have something happen, a depolarization event as a result of the channel. Indirect action via second messenger is a critical form of signaling in majority of cells that you own. A lot of molecules so here we might have acetylcholine binding, and we have what's called a G-coupled protein. And it's going to lead ultimately to the formation of cyclic AMP, which is a critical second messenger. So I know that's covered in human physiology, and I know that it's covered in anatomy and physiology as well. So when you see the reference to indirect action, the second messenger system is critical. Cyclic AMP is the critical second messenger, and it's a critical process to work at understanding, because the cyclic AMP can then be used to generate a new action potential. It can affect membrane charge. It can go, bless you all. What is this? Coughing, sneezing? What'd you do? Stay outside all weekend? I hope you did. Yeah, so there's a lot that can happen as a result of the second messenger system. Norepinephrine, okay? Excitatory or inhibitory, depending on receptors. We're back to receptors. However, whether it's excitatory or inhibitory, the receptor isn't a channel protein, but it's one of these coupled second messenger systems. Dopamine, same way. Okay? Second messengers. Second messengers become critically important. Serotonin is overwhelmingly inhibitory. Serotonin is inhibiting all sorts of pathways. Histamine goes either way as well. So what you end up seeing in here is that, oh, a lot of these neurotransmitters have actions that can be either excitatory or inhibitory. They can be excitatory and inhibitory by opening a channel protein or leading to a second messenger. Oh, second messengers, there we go. Another mode of control, the signaling. So there's a lot happening. GABA. GABA is a pretty amazing molecule. It's overwhelmingly an inhibitory molecule, and it can go either way, direct or indirect. Glutamate tends to be a direct action thing. Glutamate is an absolutely powerful molecule. Anybody sensitive to MSG? Monosodium glutamate? No? Yeah? I mean, this is something we see in people. Okay, MSG is a flavor enhancer. It's commonly used in Chinese restaurants, which is why you'll go to a Chinese restaurant and you'll see a sign up that says, no MSG used here, something like that. But when you realize that MSG, monosodium glutamate, can affect pathways in your nervous system, you realize why somebody who eats MSG and is sensitive to it, they start to feel a weird tightness in their chest. Their heart rate may start to go up because glutamate is excitatory. If you're sensitive to it, it leads to a tremendous amount of excitation. Endorphins, generally inhibitory. Substance P, generally excitatory. It doesn't have to be, it can inhibit as well. The others in here you don't have to know. But those were just, I just wanted you to have some additional information on some of the neurotransmitters that we were talking about. Now, going through the basal nuclei, we have these channels, quote, parallel channels. And it has to do with signals coming in and signals going out, and where they're relayed and what they target. So the motor channel, somatosensory input in, primary motor cortex signals in, premotor cortex signals in, they come to the putamen. From there they pass, this is the same here, okay? It's all the same. And then they pass through the ventrolateral, ventral anterior nuclei in the thalamus, go back to the premotor cortex and the primary motor cortex. This pathway primarily is involved with essentially feedback, primary motor in, primary motor out, that is going to help control the amount of movement that you see. Does that make some sense? We have somatosensory, so I have to move, I'm moving in response to somatosensation. Primary motor and premotor has to do with why am I moving and what am I moving, all right? All of these lead to, once again, going back to why am I moving, what I'm moving. So you get a feedback that says, okay, take it easy, you don't have to hit it. 100 miles an hour is too much, let's do 60. Oculomotor channel is going to affect your eye fields in the frontal cortex, okay? Parietal channels coming in, prefrontal channels coming into the caudate now. So the putamen is involved with the motor channel going to the premotor cortex and the primary motor cortex. The caudate is involved with the oculomotor, which is eye field.